Good. Good. Okay. So, good afternoon, everyone. I would like to thank Luca for the invitation and also the introduction. Today, I'm going to tell you about how we studied the 3D CFTs on the fuzzy sphere. I will mainly focus on these two papers, recent papers, and I will also cover some upcoming works and some of our older papers. So, So after an introduction to the critical gauge theories and the fuzzy sphere, I will mainly focus on two aspects. The first is the Chern-Simons-matter theory, and I will talk about a simple example of the confinement transition of the spin liquid. And then I will switch gear to the first fermionic CFT we realized on the fuzzy sphere, the free Majorana fermion. So as an introduction, conformal field theory has been a central topic to theoretical physics. In condensed-matter physics, it describes the critical behavior. In high energy, it is also used in string theories. Moreover, it tells us about some fundamental structures of quantum field theories. For example, the renormalization group flow. So focusing on the critical behavior, maybe the simplest model for a quantum phase transition is the quantum Ising model, where there is a order-disorder transition. For example, on a square lattice. If we look at the microscopic model, the symmetry is actually very small. There is only discrete space rotation and translation symmetry. However, at the critical point, when we go to IR, that the infrared, that is the low energy or long wavelength limit, there will be a much larger emergent conformal symmetry generated by translation, rotation, dilatation, and something called the special conformal transformation, SCT. So these symmetries, in return, put constraint on the operators. Now each operator must have a definite Lorentz spin under rotation, a scaling dimension which describes its transformation under dilatation. I'm muted now.
Let me check it.
I think I'm.
No, it should be okay.
Okay, I'm good. I'm good. Okay. Yeah, good. So the special conformal transformation singles out a special kind of operator called the primaries, whose 2-point and 3-point correlation functions, their forms are fixed to be some kind of power law, and the powers are related to the scaling dimensions. This set of scaling dimensions also determines the critical exponents in critical behaviors, for example, in the 3D Ising transition. Now, the conformal symmetry is known to be very powerful. In 2D, there exists an even larger, infinite algebra of conformal transformation called the Virasoro algebra. This makes many rational theories exactly solvable. Now, in 3D, although the theories are not exactly solvable, the conformal bootstrap can still determine the scaling dimensions of some theories, for example, the 3D Ising, to a very high accuracy, up to 8 or 9 digits. However, there still exists some more complicated theories that conformal bootstrap does not know so well about. One of the outstanding examples would be the critical gauge theories. Coupling complex scalars or direct fermions to gauge fields is one of the known ways to construct the interacting 3D CFTs. In condensed-matter setup, these critical gauge theories also describes many exotic critical phases or phase transitions. For example, the SO5 deconfined criticality and the direct spin liquid, which is QED with 4 flavors. However, it is difficult to obtain their critical data. As an example, under which number of flavors do these Lagrangians flow to a conformal fixed point? This is still an outstanding unsolved problem known as the conformal window problem. So to make things even more interesting, we can add some non-trivial dynamics to the gauge field. For example, we can add a Chern-Simons term to the critical gauge field. This gives us the Chern-Simons-matter theories. These Chern-Simons-matter theories, they describe transitions between or from out of topological orders. Theoretically, these Chern-Simons-matter theories, they host dualities between different interacting theories. And these theories are also very relevant to experiments, for example, in fractional quantum Hall systems or in the Moiré materials. So let us look at a very simple example of the Chern-Simons-matter theories. We take a single complex scalar, couple it to a gauge field, a dynamical gauge field, A mu, and add a level 2 Chern-Simons to it. This is a scalar coupled to U1 level 2. This describes a phase transition that is controlled by the mass m squared. When m squared is positive, the bosons are gapped, which leaves us with a pure gauge theory, which is U1 level 2 Chern-Simons. This Chern-Simons theory is known to host a semion topological order. In different contexts, it is also known as the chiral spin liquid or nu equals 1/2 bosonic Laughlin state. On the other hand, if m squared is negative, the bosons are condensed, which also hixes the dynamical gauge field, which leaves us with practically nothing. This is a depth base with no interesting feature. There's no topological order and no symmetry breaking. For example, it can describe an integral quantum Hall state. Now, a very interesting feature, as I have mentioned, of the Chern-Simons-matter theories are the dualities. Essentially, it means that different Lagrangians, they can flow to the same theory in the infrared. A very classical example would be that the scalar QED with one flavor of complex scalar without Chern-Simons, it is dual to a complex scalar or O2 Wilson fission. This is known as the particle vortex duality and has been verified numerically by Dasgupta and Harpering. But more dualities is still at the stage of conjecture. For example, it is conjectured that U1 level 1 coupled to a scalar is dual to a free Dirac fermion. The conjectures can come from matching global symmetry, matching the phase diagram, which includes the response on the ordered counterterms, and matching the operator content of both sides. Now we have mentioned U1 level 0, level 1 with a scalar, which is dual to some known theories. The simplest unknown theory here, it will be the U1 level 2 coupled to a scalar, which we mentioned on the last slide. This is conjectured to flow to a SO3 symmetric IR with 3 dual descriptions, which are U1 level -3/2 with a fermion, SU2 level 1 with a boson, and SU2 level -1/2 with the fermion. The SO3 global symmetry is manifest as the flavor symmetry for the SU2 gauge fields. For the U1 side, the manifest symmetry is the topological U1 star A, which gets later enhanced to SO3. So this theory, U1 level 2 with a boson, it appears in various contexts. For example, this U1 level 2 can be realized in spin systems on Kagome lattice or triangular lattice. This is known as the chiral spin liquid, and this theory describes the transition between a chiral spin liquid and a paramagnet. When the U1 level 2 with a scalar is realized as the transition between chiral spin liquid and integer quantum hole. Upon doping at the critical point, the lowest charge excitation would be charge 2 instead of charge 1, which favors the pairing of the of the doped electrons. This is known to induce the so-called anion superconductivity. In the cold atom setups, this transition can be realized by the Feshbach resonance. However,
sorry, in your Lagrangian, was it obvious sigma xy had to be 2, not half?
I think 2.5 would be some kind of bookkeeping or notation.
But sigma xy of the theory you wrote before is also 2 of the 2 over 4 pi ADA.
Yes, I think here if you consider only a U1 subgroup of it, the conductance would be 2. I think it also depends on what charge do you let the electrons to the flavors to have. Okay. Shall I continue? So, however, what is the nature of this transition? This is an unsolved question for 30 years, ever since its first proposal by Wen and Wu in 1993. We cannot use the quantum Monte Carlo on this system because of the intrinsic sign problem. It is also difficult to apply the conformal bootstrap. This is because for the critical gauge theories, many different Lagrangians can have the same global symmetry, and conformal bootstrap is difficult to tell them apart. So that is why we need the fuzzy sphere. It has been a very powerful method studying the 3D CFTs. It involves studying the interacting electrons moving on a sphere with a magnetic monopole at its center. Its power has been first demonstrated in the 3D Ising model, where people have obtained a wide range of spectrum with very high accuracy on small system size. And it has produced the first numerical verification of the conformal symmetry of the 3D Ising transition. So to better explain the idea, we split it into 2 keywords. First, sphere. We want a quantum Hamiltonian that is defined on a d-sphere. This is because, combined with the imaginary time direction, the cylinder, it is conformally equivalent to a flat spacetime through a Weyl transformation. This Weyl transformation maps each time slice of the cylinder to a concentric circle. So now this allows us to make use of some very nice properties of CFTs on a flat spacetime. The most important one is the state operator correspondence, which states that each CFT operator has a 1-to-1 correspondence to an eigenstate of the quantum Hamiltonian on the sphere. So the state and the eigenstate and the CFT operator, they have corresponding angular momenta. They have corresponding quantum numbers under global symmetry. And more importantly, the Hamiltonian, which sends one time slice to the other, is mapped to the dilatation operator or the scale transformation that sends one concentric circle to a larger one, which means that their eigenvalues should be corresponding. The scaling dimension of the CFT operator is proportional to the excited energy of the eigenstate of the quantum Hamiltonian. This means that to extract the scaling dimensions, we no longer need to do very complicated finite size scalings. We only need to read it from the eigenspectrum of the quantum Hamiltonian. In 1+1D, studying a quantum Hamiltonian on a circle is very easy. One only need to consider a lattice chain with periodic boundary condition. This realizes the S1 geometry. However, in 2+1D, it is much more difficult, as there is no lattice that preserves the full SO3 rotation symmetry. That's why we take an alternative approach. We instead fuzzify it. We use the spherical lambda level instead of the lattice as the single particle states. This is an idea that first comes from the quantum Hall physics, from Haldane. In fact, other people call it the Haldane sphere, but Haldane himself calls it a fuzzy sphere. That's why we use this terminology. So we consider electrons that moves on a sphere with a 4π3 magnetic monopole at its center. The magnetic field, it modifies the single particle Hamiltonian, and further the single particle eigenstates of the electrons. Now the single particle eigenstates, they form highly degenerate spherical lambda level, and the lowest lambda level has a large degeneracy of 2q plus 1. So now we can set the single particle gap to be much larger than the interaction Hamiltonian and partially fill the lowest lambda level. This means that we can constrain the fluctuation within the lowest lambda level, and we can project the system onto the lowest lambda level. That is to say, we write down the second quantized electron creation operator as a linear combination of the creation operator of the orbitals on the lowest lambda level. Now we have the single particle states. How do we construct an interacting Hamiltonian? The simplest building block would be the density operator, which is a fermion bilinear. We consider multiple flavors of fermions, so that this density operator can be put into a given representation of the global symmetry. So for example, to realize the Ising CFT, we only need to consider two flavors of fermions, which we note as spin up and spin down. So the Ising CFT would be realized through the computation between an Ising type interaction, that is a repulsion between spin up and spin down electrons, which we write as a density-density potential, and also a polarizing term, which is analogous to the transverse field. So using the fuzzy sphere, we have studied many CFTs that people do not know how to study before. For example, we have studied the SO5 deconfined criticality, and we have extended it to the SU2 QCD3. We have determined that the SU2 QCD3 flows to a conformal fixed point at large number of flavors. We can also explore new CFTs. So beyond the bulk CFTs, we study the conformal line defects, for example, the Kondo impurities, and the conformal boundaries or the boundary criticalities as well. However, all these setups, they involve a common element, that is the integer quantum Hall states, or the quantum Hall ferromagnet. On the lowest lambda level, one can realize something much more non-trivial. One can realize the topological orders with fractionally filled lambda level, lowest lambda level, or the fractional quantum Hall states. If we look at this famous experimental figure, each plateau here would correspond to a topological order. On this, we have the Laughlin states at filling 1/k, which is described by U1 level Page and Simons. We can have the Zheng sequence, the Halperin states. These are all abelian topological orders. Beyond that, we can also have the bosonic Pfaffian at boson filling 1, which is described by SU2 level 2. And we also have the Pfaffians, the Rizai sequence. This provides us with a library of topological orders. And on the fuzzy sphere, we can construct the transitions between them, which can help us study various Chern-Simons-matter theories. So now let us look at the first example, the confinement transition of the chirospin liquid, or the U1 level 2 coupled to a scalar.
I have a question
Yes.
a little bit. Why does this magnetic field not break conformal invariance for the fuzzy sphere? But you're putting a large magnetic like a large.
Yes. So the gapless operators are the fermion bilinears, which do not fill the magnetic field. So the operators that fuse the magnetic field, they are not gapless. They are not critical. And the CFT operators, they are bilinears that do not fill the magnetic field. Okay, so we want to construct the U1 level 2 with a scalar on the fuzzy sphere. We study a setup with 2 flavors of fermions and 1 flavor of boson. We let the boson experience the magnetic field as well, and let it carry twice the charge of the fermions. This means that the angular momentum of the boson is twice the fermion, and the number of orbitals of the bosons is also twice of that of the fermion. And we allow the conversion between 1 boson and 2 fermions. And the 2 flavors of fermions, they carry the fundamental representation of a SU2 flavor symmetry. On the one side, we set the fermions to be fully filled, so the fermion filling is 2, and the boson to be fully empty. Now, if we move everything to the bosonic degree of freedom, the number of particles become half, because 2 fermion go to 1 boson, and the number of orbitals become twice, so that the boson filling is a quarter of the fermion filling, which is a half. This allows us on the bosonic side to realize the one half filling bosonic fractional quantum Hall state.
Can you say again? The
Yeah.
boson orbitals are twice.
Yes, the number of orbitals for the boson is twice the fermion.
Just because its charge is twice.
I
see. So it feels twice more magnetic. The magnetic field has.
That's true. That's true. Yeah. And in our model, we write a charge density interaction, which is the simplest type of interaction we can get on the fuzzy sphere. And this term also favors the bosonic Laughlin state when everything is bosonic. We allow a boson-fermion conversion between 1 boson and 2 fermions. And we also tune the tuning parameter is a relative chemical potential, which tells us whether we favor fermions or favor bosons. When mu is large negative, the fermions are favored, so it will be a fermionic integer quantum Hall state. When mu is large and positive, the bosons are favored, and it is a bosonic Laughlin state. Theoretically, we can show that this transition can be described by the 4 dual Lagrangians. We can match the phase diagram, meaning that we can match the topological order on both sides, and also match the response. This includes the Hall conductance given by the Chern-Simons term of the probe field, and also the thermal Hall conductance, which is given by the gravitational Chern-Simons term. So numerically, we carry out an exact.
So these theories have what SU2 global symmetry?
The lower two has SU2 global symmetry.
The H field is not a billion, the lower two?
Yes, we set alpha and beta to be SU2 H fields.
I see. So does it have a SU2 global symmetry?
Yes.
What is the what is the global symmetry? That it looks like the SU2 is gauged. Or am I reading it wrong?
Yes, I think if you write it as a real degree of freedom, you can see it more clearly. So the thing is, SU2 gauge fields are a special case. SU2 coupled to n flavors has SPN symmetry. So it will be clearer if you write it as two real components instead of one complex component.
Okay. So here in the third line, your scalar has two complex components in the fundamental of.
It's yes, it is fundamental under the SU2 gauge field.
Okay.
Shall I continue? Okay. So numerically, we carry out the exact diagonalization calculation with our package quantified. The first thing we observe is that the observables, they change continuously as we tune the tuning parameter mu. And the energy gap closes at a critical point. That means that the spin gap, it scales with 1 over r, where r is proportional to the square root of the number of orbitals, which is the radius of the sphere. And the charge gap, since the charge U1 symmetry decouples from at the critical point, remains a constant. So the more important piece of information, besides being continuous, is the emergent conformal symmetry. Remind you that we extract the information about conformal field theory through the state operator correspondence. Each CFT operator has a corresponding eigenstate of the fuzzy sphere model. So a very outstanding feature of the CFT spectrum is the conformal multiplets. If we start from a primary, if we act spatial derivatives to it, we get its descendants. For example, if we act partial on S, we get partial S, which is spin 1 and scaling dimension delta plus 1. If we act again, we get bot S and partial S at delta plus 2 with spin 0 and spin 2, etc. Practically, from our numerical results, we find that all the lowest lying states can be classified into such conformal multiplets, and all the descendants of the lowest lying primaries can be identified. For example, for S, we can find all of its descendants. For the symmetry current J as well, the descendants can also have the epsilon tensor structure. And for some higher operator, we call T here, we can also identify its descendants. For example, this primary is at scaling dimension about 5. So how do we know that these states that form integer spacing are the descendants of the same primary? We can measure the quality of the descendant states by the conformal generators. And the generator P mu plus K mu, it can be constructed by integrating the Hamiltonian density with the coordinates. This P mu plus K mu, when it increases or decreases the number of derivatives by 1. For example, acting on S, we get partial S. Acting on partial S, for the spin 0 component, we get S and bot S. For the spin 2 component, we get partial S. If we compare the left-hand side and the right-hand side, we take their overlap. The overlap closer to 1 would mark better conformal symmetry. And indeed, we find that all these lowest lying overlaps are above 98%, most even above 99%, which also tells us about the conformal symmetry. Now, having established the conformal symmetry, the next question we want to ask is about the operator spectrum. So how does the spectrum of this CFT look like? The most important piece of information would be the lowest lying singlets. What we have found is that there is only one relevant singlet operator, this S. We extract its scaling dimension through finite size scaling at 1.52. And the second singlet is way above 3, around 3.7. So this marks a genuine criticality. And delta S also gives us the scale, gives us the critical exponent mu. And this fact is consistent with dualities with annual superconductivity. And the fact that delta S is less than 2 also tells us that this transition is unstable against disorder. Beyond the lowest, yes.
What's the statement? It's consistent with duality. What does that mean?
Yes.
The numerical value?
Yes. So the fact that because the duality has two descriptions with SU2 and 2 descriptions with only U1. So one necessary condition for the duality is that the anisotropy is irrelevant. The flow from so the U1 gauge theory, the U1 descriptions are also stable against the
SU2, the charged operators.
Yes. So this can be verified from our operator spectrum.
So what does the left figure mean?
Yeah, well, we take different parameters. So each line, so we take different parameters and determine the critical point, and extract the scaling dimension at different parameters. So each line, we are tuning an irrelevant operator, and we find that these lines scales towards the same scaling dimension. This is the value we report.
It seems that the different lines kind of deviate from each other.
That's true. The difference from each line is that we tune an irrelevant operator. The effect of the effect of these irrelevant operators will diminish at larger system size. So that's why we see they scales to the same value.
Well, I should read from right to left.
Yes.
I see.
The left is the value we extract.
I see.
Yeah. So the n to the power minus half. So this is infinite size.
Thank you.
This is the value we extract. Yeah. So we can also look at the higher spectrums, which carries the flavor SU2 to spin. This is the flavor SU2 spin, and also the Lorentz spin L. So we actually find that these operators are very high up, which allows us to use these as an input we put into conformal bootstrap. So each higher operator here can be used as a gap for conformal bootstrap to exclude some other theory, some competing theories. The sparse higher spectrum makes this theory now a very suitable target for the conformal bootstrap with the additional information input from the fuzzy sphere. So as a brief partial summary, we have studied the confinement transition of the chiral spin liquid. This theory has 4 dual Lagrangian descriptions and appears in various contexts, for example, the annual superconductivity. On the fuzzy sphere, we realize it as the transition between nu equals to 2 integer quantum Hall state and nu equals half Laughlin state. We find numerical evidence for continuous transition and conformal symmetry. And we find that there is only one relevant operator besides the conserved current, and we extract its scaling dimension. This is the first study that reports the conformal symmetry and the critical data for a Chern-Simons-matter theory, thus also concluding the mystery for 30 years. So what can we do next? The first thing, we can consider the conformal defects of the gauge theories. The fuzzy sphere is a natural platform to study the conformal defects. If we look at the path integral configuration, the defect is just a line passing through the origin point. And after the radial quantization, after transforming it to a cylinder, this just becomes two impurities at the north pole and the south pole of the fuzzy sphere. So what we need to do is only to put something on the north pole and south. Now for this theory, each gauge theory description admits a Wilson line operator, which also serves as a line defect if you add it to the action. For the U1 descriptions, there are also vortex lines. So how do we construct these on the fuzzy sphere? We should make use of the information about the defect endpoint operator. For example, take the SU2 Wilson line as an example. This line ends at a gauge charge, which carries the SU2 fundamental. So what we need to do is to put a SU2 spin half at the north pole and south pole and couple it to the bulk. This is literally a Kondo impurity. So this theory is a natural platform to study the conformal defects. So we can also ask, are there other transitions out of the gyrospin liquid? It has been proposed a zoo of CFTs between the gyrospin liquid and, for example, the Neo and the superfluid, which spontaneously breeds the SO3 and SO2 symmetry. And further, a transition between gyrospin liquid and SO5 SSB, which flows to these two theories. Each of these transitions is proposed to be described by some kind of Chern-Simons-matter theory. And to realize this, for example, the transition between gyrospin liquid and SO5 SSB, on the fuzzy sphere, we only need to replace the number of fermions to 4 flavors and let them carry the sp2 fundamental or the SO5 spinner. So now, when mu is smaller than mu c, the mu equals to 2 integer quantum Hall states become a state that has SO5 spontaneous symmetry breeding, and thus we can realize this transition between gyrospin liquid and SO5 SSB. And by turning on an anisotropy, we can let it flow to the other theory. So moreover, we are also developing a general framework for QED with Chern-Simons. So we can consider the transition between U1 level n and U1 level n. It is described by U1 level m plus n over 2 coupled to n minus m fermions. On the fuzzy sphere, we can realize this theory as the transition between 1 over n Laughlin state and 1 over n Laughlin state up to some fermionic integer quantum Hall spectators. This framework includes the gyrospin liquid confinement, which has m equals 1 and n equals to 2. We mentioned before. And this also includes some theories that we are very interested in. For example, the direct spin liquid, which has U1 gauge field with no Chern-Simons coupled to 4 flavors of fermions. Moreover, we are trying to develop a more general framework that studies the transition between Zheng states instead of the Laughlin states. Experimentally, they are relevant to the Moiré materials. So it seems that on the fuzzy sphere, we can answer many questions about the Chern-Simons-matter theories, about the CFTs. But there left a question that we haven't answered yet. that is the questions of the QFT instead of just in the IR. For example, given a QFT Lagrangian, what is IR fate it will flow to? Given two Lagrangians, how do we know whether or not they are dual to each other? So far, we can only realize the IR theory with the fuzzy sphere. But how do we realize the Lagrangians? We do not know yet. On the other hand, fuzzy sphere is actually a very suitable platform to regularize QFTs. This is because the non-commutativity, it sets a very natural cutoff scale. So on the fuzzy sphere, the local operators and the correlators, they are all non-divergent. And this leaves us with the question, how do we translate the Lagrangians to the fuzzy sphere models? So people have already realized the free scalar theory. This is the first step. It is realized on two flavors, and the fields pi and phi, for example, they are all simply written on the fuzzy sphere, and the Hamiltonian is also very analogous to the field theory Hamiltonian. So following this roadmap, how do we realize the free fermions? How do we realize the gauge fields? And how do we couple them together? For example, the Yukawa coupling between the scalars and the fermions, or the minimal coupling between the free fields and the gauge fields. So let us focus on the next step, the free fermions.
So it wasn't free, I mean, using all these 3D kind of bosonization dualities, wasn't free Dirac in one of these?
Yeah, yes, but we want more intuitions into how the fermions are written on the fuzzy sphere. And so far, the theories we have written are all purely bosonic theory.
Okay, I see.
Which means that they have no critical fermions.
Mm-hmm.
So there are actually more reasons for studying fermionic CFTs. For example, some theories can have enhanced supersymmetry. One example would be the Ising model coupled to a Majorana fermion, which is also known as the super Ising theory, with an enhanced n=1 SUSY. The Ising field sigma, the Majorana fermion, chi, and the epsilon, they form a supermultiplet, and their scaling dimensions are locked to each other. These fermionic CFTs are also easier to detect experimentally. For example, the electric conductance is a universal quantity at the critical point, which is given by JJ-OPEs. For example, the topological transitions between the Zheng states, they are experimentally relevant to the Moiré materials, and they are theoretically described by the 2D Chern-Simons. But before all these, let us focus on the simplest instance, the free Majorana fermion. So it is actually hard to realize a fermionic CFT on the fuzzy sphere. As I have said, before this work, all the CFTs realized on the fuzzy sphere are purely bosonic. So the difficulty is that the microscopic fermions on the fuzzy sphere, they actually experience strong non-commutativity, and they carry projective wraps of the rotation symmetry. This forbids them to flow to CFT operators. Our solution, again, is to use a boson-fermion mixture. We consider one flavor of fermion and one flavor of boson on the fuzzy sphere. So that now their local bilinears, F dagger B and B dagger F, they have no electric charge, so it can flow to the CFT operators. It carries fermionic statistics. And we can set the number of orbitals for the fermions to be one more than the boson orbitals. So in this way, the fermion and boson can have a angular momentum mismatch of 1/2. This also allows the f delta b operator to have half integer angular momentum. So we consider the total filling to be 1. So the fermions, when the fermions are favored, this is an mu equals 1 fermionically integer quantum Hall states. And the boson, when the bosons are favored, the boson is at filling 1. This can realize a bosonic Pfaffian state, as you described by SU2 level 2. And for the bosonic Pfaffian state, it happens that its number of electrons is 1 more than the number of orbitals. So we realize this transition through a electric density interaction again, and a double conversion between 2 fermions and 2 bosons, and a relative chemical potential, which tunes this transition. So interestingly, on the phase diagram, we find an intermediate phase with 2 continuous transitions. So at the first transition, both the fermion gap and the boson gap closes. And at the second transition, the fermions remain gapped, and the bosons, it is gapless. So it is a purely bosonic theory. So what is the nature of this intermediate phase? It is actually a F-wave topological chiral superconductor. What we need to know about this state is that it is an invertible T2FT with a Chern-Simons description SO3 level 1. Its chiral central charge is 3/2, and it has 3 chiral Majorana fermions on its edge. These edge modes can be verified through the entanglement spectrum. There has been a Li-Hao-Dan conjecture that the entanglement spectrum, it has a 1-to-1 correspondence with the edge modes that is on the physical edge. And on the entanglement spectrum, we can indeed observe the spectrum of 3 chiral Majorana fermions. So now we can consider what is the two transition between them. So the first transition is between the integer quantum Hall state and the topological superconductor. It is a transition with a gravitational Chern-Simons jump of 1/2, and between 2 invertible T2FTs. So naturally, it is described by a free Majorana fermion theory. So numerically, we indeed verify the spectrum of the Majorana fermion. The theory has both half integer spin and integer spin operators, and these states sit nicely at integer level in accordance with the spectrum of Majorana fermion. And all these levels under finite size scaling, it goes to the expected value. So the local fermions, it is realized as the boson-fermion bilinears on the fuzzy sphere. We can write the 2-component spinor of the Majorana fermion as one component is B dagger F and the other is F dagger B. And the form of its correlators is fixed, which is indeed verified numerically on the fuzzy sphere. One interesting thing is that if we consider this realization of Majorana fermion and rewrite the Hamiltonian with it, we actually find that the fuzzy sphere Hamiltonian, it has exactly the same form as the QFT Hamiltonian of the Majorana fermion, in addition to a density-density interaction. And we find that the critical point, it sits exactly at mu c equals 0. So it seems that it is protected by. Yes.
Wait, you want to interrupt the sentence?
Yeah. Yes. It seems that it is protected by some hidden symmetry. but we are yet to discover what this symmetry is. Yes.
So at this Majorana CFT,
Yes.
the boundary, do you expect to see chiral edge modes? And if so, could you see that with your method?
We haven't tried that yet. We haven't tried to look at the well. But the two phases, for example, the F-wave superconductor, it can be interpreted as three gapped Majorana fermions. And we indeed see three Majorana fermions on its edge. This can be verified, for example, from the degeneracies.
Can you actually look at the entanglement spectrum also at the critical point?
We haven't tried that yet, but I believe it is possible. But again, at the critical point, it's not sure whether or not it corresponds to the physical boundary. Because this conjecture only holds for the QFTs. Okay, so we have found that the Hamiltonian on the fuzzy sphere has the same form as the Hamiltonian of the quantum field theory. Can we extend this analogy? For example, can we extend the analogy to the interacting theories? Can we realize the super-Ising theory in the same way? We can construct three flavors, two fermions and one boson. We can identify the hopping between the boson and F0 as the Majorana fermion, and the hopping between these two fermions at the Ising field. In this way, each term in the interacting Lagrangian of the super-Ising can be translated into a full operator term in the on the fuzzy sphere. In this way, we are pushing towards a dictionary between the Lagrangians and the fuzzy sphere model. Also, can we realize the gauge fields, which are spin 1 fundamental fields in a similar way, with an angular momentum mismatch, not by 1/2, but by 1. So coming back to the phase diagram, there is another phase transition between the topological superconductor SO3 level 1 and the bosonic Pfaffian state SU2 level 2. These two theories actually only differ by gauging the D2 center. So it falls into the gauged Ising universality. And
can I ask about super-Ising on your previous slide?
Yes.
So here you're trying to realize the whole QFT, right? Which is an interesting way to do it. But in your previous examples, you didn't really need to do that, right? You just kind of studied the phases you have on information and the CFT. So is there a way to, is there maybe an easier way to get this supersymmetric CFT by, analyzing its phase structure and just coming up with a model that doesn't necessarily, have Majorana fermion does simple collected,
we think that this would be the simplest way.
Okay.
One thing is that the Majorana fermion, it has the parity anomaly, and we cannot actually realize the parity symmetry on the fuzzy sphere. So without this symmetry, it actually has a lot of relevant operator or tuning parameters. We need some guiding principle of how to design this model with many tuning parameters. And the analogy with the Lagrangian is, we think, the best way to do it.
Because so this CFT would have like three relevant.
Yes. So we have to tune sigma, we have to tune epsilon, and we have to tune sigma prime.
I see. Is there a way to realize a subgroup of supersymmetry exactly?
That's an interesting question. We have proposed a way to realize the n equals to 2 supersymmetry, where part of the U1R can be realized. Yeah. This is an idea called the fuzzy supersphere we are working on. So the global symmetry is no longer SU2, but OSP1/2. So it can serve as a larger subgroup of the superconformal group.
Can I also, is it possible to also get these gross and Will-Yukawa theories? I guess using like a special case.
Yes, I would think it's possible.
Okay. So it would be like similar to this.
Yeah, you just need complex fields everywhere. Yeah, so it's a gauged Ising CFT. The local op between the SO3 level 1 and the SO3 level 2. So the local operators are the Z2 even sector of the Ising CFT. The Z2 odd sector of the Ising CFT is no longer local operators, but they are endpoints of the Z2 Wilson line, which we can also see on the fuzzy sphere.
What's the mess of brown circles?
It's a mess. It's the charged excitations that you may like.
I see. Okay.
So,
that's probably the UV cutoff, right, of the CFT.
Yes. The thing is, some of the excitation, the softest excitations are in the boson-fermion state. For example, the rotors, the magnetic rotors can come into the spectrum. And what we can do is that we can verify that these brown dots, they scale to infinity in the finite size scaling. But at small system size, it is actually very messy.
But you trust, so for example, on your left picture, the lowest brown dot is 2, right? Delta equals 2 roughly.
The lowest brown dot?
Yeah, the lowest brown circle is pretty low.
Yes, here.
No.
Here.
Yeah, this one, right?
It's 2.5.
Yeah, but it's like a dimension equals 2 roughly.
Yes.
So are you trusting CFT data beyond 2?
So the thing is, we know this theory only has bosonic operators. So these brown dots at half integer spin, you can neglect them. This sector does not appear in the CFT. So the lowest operator at the lowest brown dot at integer spin would be here. So, yeah. So that's the scale that really comes into the mass.
Can you see the leading spin 4 operating?
Leading spin 4? Sorry?
Like, well, I guess in this plot, you don't. Can you see the leading spin operator in here?
The spin 4.
Yeah.
Yeah.
5.
So the rotor, it has the lowest spectrum at larger L. So what we do is we don't trust the operators from at higher L.
Okay.
At higher spin. We only trust our lower spin data. But again, this is at quite small system size that is reachable by ED. And if we do DMRG, it's possible that we get much more trustworthy data. Yeah. So I would like to acknowledge my collaborators, my supervisor, Inchen He, and my collaborators at Perimeter, Davide Gaiotto and Chong Wang. So this talk today is mainly based on these two papers with them. And as a final summary, we have studied the first Chern-Simons-matter theory, which is the confinement transition of the tyrosine liquid. It is described by U1 level 2 with the scalar and dual descriptions. We find on the fuzzy sphere that this transition is continuous and conformal, and there is only one relevant singlet. We extract its scaling dimension. It opens up the possibility for many ongoing directions. For example, the defects of the gauge theories, the other transitions out of tyrosine liquid, and a general framework for 3D with or without Chern-Simons. And also, we have realized the first fermionic CFT through a boson-fermion mixture, and the local fermions are realized as their bilinears. And the Hamiltonian is actually analogous to the field theory. we have been pushing towards extending it to interacting fermionic CFTs and the realization of Lagrangian QFTs. The final message today is that we are building a connection between fuzzy sphere and the fractional quantum Hall effects. Using the fractional quantum Hall effects, we can realize many interesting transitions between topological orders on the fuzzy sphere. And in return, the fuzzy sphere can help us answer many questions about the fractional quantum Hall transitions that has been standing for decades. And I noticed that all these setups today involves both bosons and fermions. So I guess this is really a boson-fermion butterdo. Thank you.
Questions for Zheng?
Yes.
Sorry, can you give me a concrete example of how non-commutativity set a natural cutoff scale?
So the non-commutativity, essentially, it gives us a scale that, for example, for the for example, the magnetic length. So it actually says that below this scale, you cannot distinguish the points from each other.
Oh.
Yeah. So that's why it becomes fuzzy or blur. So this gives us a minimal scale at which we can distinguish the points apart.
So, like for the lowest Lagrange level, I guess you have something that depends on B.
Yes, yes. It's a magnetic length depending on B. Yes.
Have you also done the Dirac fermions?
We are trying to push it towards Dirac fermions.
Would it not be easier than Majorana?
It will essentially be two Majoranas.
In your Majorana case, you got the Majorana CFT, but the whole phase diagram does not look like a Majorana fermion. For a Dirac, you can presumably do the whole phase diagram as a Dirac.
Yeah, I mean, it is somehow similar to a Majorana phase diagram. On the one side, on the one side we have two gapped Majorana fermions. On the other side we have three gapped Majorana fermions.
Right, but you never have one in zero.
Yeah, having a background is allowed.
Is allowed. Okay, I see.
The background does not mess up with things.
And the gap is smaller than the gap to the next Landau level, so that's
Yes, we always said that.
yeah.
I mean, as a follow-up question, I guess the background doesn't affect the bulk physics,
Yes.
but the boundary would, like if you want the boundary phase diagram of the Majorana CFT, now you would have the background chiral mode.
Yes, I guess that is true. The boundary may feel the background. Yes.
Okay, if there are no more questions, let's thank Zheng again.